a recording of the session today, a copy of the PowerPoint that Anna's going to use, and also some additional homework questions. Those are for you to work on independently. And then Friday, if you need some help with some of those, we have an open drop-in session from 10 a.m. to 1 p.m. You use the same link that you used this morning to log in, and we'll be there to help you out if you have any questions about any of the homework questions or need some further instruction. Okay. So does anybody have any questions?
No, thank you.
Okay, I could barely hear you, Brianna, but just as a FYI. So if you guys have a question during the session or a comment, if you don't understand something, feel free to raise your hand, use the little icon at the bottom of the screen, or type it into the chat, and either Anna or myself will address you. Okay? So Anna, if you're ready, let's go ahead and get started.
Yes. Okay, let me start the presentation. Can you guys see the screen? Yes? No? Maybe?
Yes.
Awesome. Alrighty. Then, so this is the math review for third semester, which is the maternal, neonate, and pediatric nursing math. So this semester, for math at least, is one of the more challenging ones. I'm not going to lie to you, which means it's really good that you guys are here because it needs a lot of like getting familiar with the new formulas and everything. So just letting you guys know. So the things we need to know. We need to know the properties of percent solution and concentration ratios. The microdrip tubing is 60 drops per minute. The calories in dextrose and glucose are for each 4 calories per gram. Technically, it is 3.4 calories per gram, but generally when you use it in a formula, we use 4 calories. And then we also need to know the formulas for MAP, BMI, BSA, IBW, the calorie needs, fluid needs, and rehydration needs. As a note, the IBW, the calorie and fluid needs differ from men to women, pregnant women, and children and infants. So we have to tweak the formulas for each depending on the gender and age of the patient. And also recall that when dividing fractions, you have to flip one fraction, the bottom fraction, and multiply. So for example, let's say the problem says it's milligrams per kilogram per day. If you wanted to write it as a fraction, it would be like milligrams per kilogram, all of that divided by day. Now, if in the bottom you don't have a fraction, it is the same as having it over 1. So it could be rewritten as milligrams per kilogram divided by day over 1. Now, when you're dividing by a fraction, it is the same as multiplying times the flipped fraction. So you could rewrite it as milligrams per kilogram times 1 over day, which just goes into milligrams over kilogram times day. So just to let you know, like if you see milligrams per kilogram per day, it is the same as milligrams over kilograms times day. And also some common equivalences. 1 cubic centimeter equals 1 milliliter. 1 ounce is 30 milliliters. 1 teaspoon is 5 milliliters. 1 tablespoon is 15 milliliters. And 2.2 pounds makes 1 kilogram. The properties of percent solution and concentration ratios. So a solution with X% strength is made as X grams in 100 milliliters of sterilized water. For example, if you have 5% dextrose in water, which is the D5W, it means it is 5 grams of dextrose in 100 milliliters of water. If you have D7.5W, means 7.5% dextrose, which is 7.5 grams of dextrose in 100 milliliters of water. As well, if you have 0.9% normal saline, it means there is 0.9 grams of salt, NaCl, in 100 milliliters of water. Then, if you have a X to Y solution, it means it is made of X grams and Y milliliters of sterilized water. So for example, if you have a 1 to 2,000 epinephrine solution, it means it has 1 gram of epinephrine in 2,000 milliliters of water. And if you have a 50 to 10,000 saline solution, it means you have 50 grams of NaCl in 10,000 milliliters of water. Units. Sometimes some units are not specified, so we have to know how to kind of read into the problem. So if for a liquid medication, if it is given in the hospital or given by a nurse, we're gonna assume it's in milliliters. If it is at home, we're gonna have to work it in terms of teaspoons. And for IV infusion, if it's a pump, the flow rate is in milliliters per hour, and the drop rate is in drops per minute. Drops per minute can be written as GTT or GTTS, is the same thing. Then for rounding, some measurements have to be rounded to a whole number. For example, capsules, vials, and drops. For tablets, generally you round to the nearest whole, but if the problem specifies the tablet is scored, then you may round to the nearest half or quarter tablet. For teaspoons, you have to round them to the nearest quarter. There are also some extra rounding rules in the nursing handbook, and also some of your instructors may have their own particular rounding rules, so it's just a matter of asking them if they have any particular specifications for you to round your answers. Any questions up till now? No? Okay. Then let's go through some walkthrough problems. The doctor ordered 30 grams of magnesium sulfate in 1,000 milliliters of fluid. The loading dose is 5 grams in 30 minutes. How many milliliters per hour will the nurse set the IV rate for? Round to the nearest whole number. So first we have to read what we have to then figure out what we need. So in this case, our order is for 30 grams in 1,000 milliliters. And the loading dose is 5 grams in 30 minutes. Now, what are we looking for? The problem is asking us to find milliliters per hour. So we write milliliters per hour equals to, we want milliliters on top, so we would write 1,000 milliliters over 30 grams. We have to get rid of grams, so we multiply times 5 grams over 30 minutes. And we want our answer in terms of hours. So we multiply times the conversion ratio of 60 minutes over 1 hour. To check the units, the grams and the minutes cancel out, and we are left with the units we want, which are milliliters over hour. So we just multiply the numbers on the top, multiply the numbers in the bottom, and then divide. So we would have 1,000 times 5 times 60 divided by 30 times 30, which would give us, when rounded, 335 milliliters over hour. Okay. Disclaimer, I'm not a nurse, so I'm probably gonna butcher most of the names for the medications, so forgive me for that, but I know the math, so that's what matters to me. Okay, so calculate the total milligrams of gentamicin sulfate received in 48 hours. The order is 2 milligrams per kilogram every 18 hours IV. The infant weighs 3,200 grams. So what is the order? Our order is for 2 milligrams per kilogram per dose. And there is 1 dose every 18 hours. And the weight of the infant is 3,200 grams. Now, what are we looking for? We're looking for milligrams in 48 hours. So we're going to write milligrams equals 2. Since we want those on top, we would write 2 milligrams over kilogram per dose. We want to cancel out the doses, so we multiply times 1 dose over 18 hours. Then we want to get rid of the kilograms. Since our weight is in grams, then we use a conversion factor of 1 kilogram over 1,000 grams. Then multiply times the weight, which is 3,200 grams. Note, remember that whenever you have a number that is not a ratio, that is not a fraction, we use a 1 as a placeholder. It depends on which way you want to write your fraction. For example, here we want the grams on the top, so we would write a 1 in the bottom as a placeholder. If you needed your number to be on the bottom, then you would put a 1 as a placeholder on top. And so we check the units. And we want to know how many milligrams in 48 hours. So since the hours are in the bottom, we multiply times the hours on top. So we check the units. The doses, kilograms, and hours and grams cancel out, and we are left with only milligrams, which is what we want. So we multiply and divide. So 2 times 3,200 times 48 divided by 18 times 1,000, which gives us 17 milligrams. Questions? Okay. Calculate the milligrams per dose for an infant who weighs 6 pounds 7 ounces, who has an order for ampicillin 125 milligrams per kilogram to be divided into 4 equal doses. Okay, so our order is 125 milligrams per kilogram divided by 4 doses. And the weight of the infant is 6 pounds 7 ounces. We are looking for milligrams per dose. So first of all, we have to have the weight as one single number. So here we have like in terms of pounds and ounces. So what we're going to do first is convert those ounces to pounds so that we have it together as a single number. So we write pounds equals 2, then the conversion ratio, which is 1 pound over 16 ounces, times the 7 ounces over 1 as a placeholder. The ounces cancel out, and we are left with 0.4375 pounds. To this, then we add the 6 pounds. So in total, the weight of the kid is going to be 6.4375 pounds. Now we go into what the problem is asking us for. So we're being asked milligrams per dose. So we put the milligrams on top. We have 125 milligrams per kilogram. To cancel out the kilograms, since our units are in terms of pounds, we use a conversion factor, 1 kilogram over 2.2 pounds, then multiply times the weight, which is 6.4375 pounds over 1. And we want to cross out, well, to add the doses. So times 1 over 4 doses. We cross out the units, we're left with milligrams over doses. And so we work with the numbers. 125 times 1 times 6.4375 divided by 2.2 times 4 gives us 91.4 milligrams per dose. Or in the way we wrote the order is 125 milligrams per kilogram per 4 doses. So that means we could write everything as a single fraction itself. So instead of having like this fraction and this fraction, we could just write it as 1. So it would be 125 milligrams per kilogram per 4 doses. And then we would multiply it times the conversion ratio for kilos and pounds times the weight. And it would still give us the same 91.4 milligrams per dose. It depends on you, whether you want to put it as a single fraction or if you prefer to write it as 2 separate fractions. That is up to you, but just know that you could write it either way. Okay, so now we have to calculate the patient's BMI, which is the body mass index. The patient's weight is 120 pounds and her height is 5 feet and 8 inches. So just as we did for the weight, we need our height in terms of just one unit. So we have to convert the feet into inches. Why? Because our formula for BMI needs the number in terms of inches. So we put inches equals 2, and then our conversion ratio, 12 inches over 1 foot times 5 feet over 1, which gives us 6 inches. To that, we add the 8 inches. So in total, the height of the patient is 68 inches. Now we go into the BMI formula, which is BMI equals the weight in pounds times 703 divided by the height in inches squared. So for this patient, it would be the BMI is equal to 120 times 703 divided by 68 squared. And once you put that into your calculator, you get 18.24. And if we round to the nearest decimal, then we look at the one before, which is a 4. 4 is lower than 5, so we round down to 18.2. Questions? Okay. If the adult dose of a medication X is 400 milligrams every 6 hours, what is the dosage for a child who is 35 inches tall and weighs 28 pounds? So here we have to use a formula which converts from adult dose to child's dose. But first, for that formula, we need the BSA, which is the body surface area. So for this, we need the square root of inches times pounds divided by 3,131. So in this case, the BSA for this child would be the square root of 28 times 35 divided by 3131, which would give us a BSA of 0.56 meters squared, which is the units for BSA. Now we go into the formula for finding the child's dose. So to find the child's dose, you would multiply the child's BSA times the adult dose and divide it by 1.7 meters squared. So in this case, the child's dose is 0.56 meters squared times the 400 milligrams divided by 1.7 meters squared. The meters squared cancel out, and once we multiply and divide, we get that the child's dose is 131 milligrams. Now, let's go into calories. So, to calculate the amount of calories a newborn has received per kilogram per day, we have that the newborn is receiving Similac 24 milliliters every 4 hours, and Similac is 20 calories per ounce. And the newborn is also receiving an IV of dextrose 5% at 3 milliliters per hour. And the newborn currently weighs 6 pounds and 3 ounces. So we have to write our information. So as you can see, we have 2 sources of calories here. So we're going to have to work with each one independently. So for the Similac, we have 24 milliliters per 4 hours and 20 calories per ounce. For the IV, we have 3 milliliters per hour and 5 grams in 100 milliliters. Because remember that when you have the D5W, it means 5%, which means 5 grams in 100 milliliters of water. And then the weight of the baby is 6 pounds and 3 ounces. So let's go first with the Similac. So we are looking for calories per day. So we want calories on top. We put 20 calories per ounce, but we have the volume in terms of milliliters. So we want to use a conversion ratio of 1 ounce over 30 milliliters, then times 24 milliliters every 4 hours. Since we want it in terms of days, we multiply times 24 hours over day. Our units cancel out and leaves us with calories per day. So we multiply the numbers on the top and divide by the numbers on the bottom, which would be 20 times 24 times 24 divided by 3 times 4. 30 times 4, which gives us 96 calories per day. Now, that is from the first source of calories. For the second one, the IV, so the dextrose 5%, we want to find calories per day. So we multiply it times the caloric value of dextrose, which is 4 calories per gram. Then multiply it times the percentage, which is 5 grams over 100 milliliters, times the rate of the IV, which is 3 milliliters per hour, and then multiply times 24 hours in a day. Our units cancel, and so we just multiply and divide the numbers. So 4 times 5 times 3 times 24, and divided all of that over 100 gives us 14.4 calories per day. Then we look at the question. Our question is, calculate the amount of calories the baby has received per kilogram per day. So our total calories are 96 plus the 14.4, which is 110.4 calories per day. Now, since we want it per kilogram, then we use the weight of the baby, but we need to convert those 3 ounces into pounds to have a single number. So we need to convert it and put pounds equals to conversion factor 1 pound over 16 ounces times 3 ounces over 1 as a placeholder. Ounces cancel out and we are left with 0.1875 pounds. To that we add the 6 pounds, so the total weight is 6.1875 pounds. And so we want to calculate calories per kilogram per day equals to, so we had solved for the calories before, so 110.4 calories per day times, we need kilograms on the bottom, so we would add our conversion factor of 2.2 pounds over 1 kilogram, and then multiply times the weight. As I had mentioned before, the one that you need as a placeholder depends on whether you want your units in the bottom or in the top. In this case, we want the pounds in the bottom so that they can cancel the top. Therefore, that's why we put the 1 on top and the pounds on the bottom. So then the pounds cancel out. We multiply and divide. So 110.4 times 2.2 divided by 6.1875 gives us 39.3 calories per kilogram per day. Questions? This problem in particular has many steps, so I know it can be confusing, but it's just a matter of taking your time and looking at what you have, what you need, and all of that. Also, a little note, you can include the weight in the dimensional analysis, or you can do it separately. So for example, you could have converted this weight of pounds into kilograms separately, or you could add it here. That is however you prefer. Calculate the calories needed per day. The female patient is 5 foot 4 inches and weighs 135 pounds. So our information for the height is in 2 units again. Oh, sorry. So to calculate the calories needed per day, we need the IBW, and the IBW of a woman, the formula is 45.5 kilograms plus 2.3 kilograms times inches over 5 feet. And then the adult calorie needs per day equals to the IBW times 30 minus 35 calories. So in this case, it is good that we have the height separate and feet in inches, because that way we know straight away that the inches over 5 feet are just 4 inches. So we calculate the IBW, so equals to 45.5 kilograms plus 2.3 kilograms times the 4 inches, and that equals to 54.7 kilograms. We plug that into the adult calorie needs, which are 54.7 times 30. Oh, it isn't minus, it is a range, my bad. So it is 54.7 times 30, which is 1,641 calories per day. And the higher end of the range is 35, so 54.7 times 35 gives us 1,914.5 calories per day. So that means that our range of calories needed for this person is 1,641 to 1,915 calories per day. Questions? All right, let's go into calculating the mean arterial pressure, which is MAP. So the blood pressure is currently 180 over 110. Our formula is MAP equals systolic plus 2 times the diastolic divided by 3. So we plug in our numbers. So our systolic is 180 and our diastolic is 110. So 180 plus 2 times 110 divided by 3 gives us 133 millimeters of mercury. Now, calculate the milliliters per hour for a patient experiencing a postpartum hemorrhage. The order is to infuse 150 milliliters per hour with additional fluids based on hourly losses. The urinary output is 100 milliliters. The vaginal bleeding is 110 milliliters during the last hour. What should the IV be set for the next hour? So the order is for 150 milliliters every hour, but we have to consider the additional fluid losses. So, 150 plus the amount of urine plus the blood loss, which is 150 plus 100 plus 110, which gives us 360 milliliters per hour. So that should be the IV rate for this person. Questions? Okay. Calculate the milliliters per day and calories per day for a 4-month-old. The intake is 105 milliliters, 110 milliliters, 105, 125, 110, 20, and 30. And the formula is 20 calories per ounce. So first we have to add all of those intakes. When you add all of that, it gives us 715 milliliters per day. And we want to calculate, okay, so that is for the first part of the question, which is to calculate the milliliters per day. And now we calculate the calories per day. So we put calories per day equals to, we put the caloric value, which is 20 calories per ounce. We have our units in milliliters, so we use a conversion ratio of 1 ounce over 30 milliliters times the 715 milliliters per day. Our ounces and our milliliters cross out, and we are left with 20 times 715 over 30, which gives us 476.67 calories per day. A neonate who is term, 1 day old, and weighs 7 pounds and 7.5 ounces requires an intake of how many calories per day? So first we convert the ounces to pounds using the conversion ratio. So pounds equals to 1 pound over 16 ounces times 7.5 ounces over 1, which is equal to 7.5 divided by 16, which is 0.46875 pounds. To that, we add the 7 pounds, so the total weight is 7.46875 pounds. Now, to calculate the calories per day, we have a formula of 100 calories per kilogram per day. To that, we had to get rid of the kilograms. So since we have our number in terms of pounds, we add the conversion factor of 1 kilogram over 2.2 pounds times 7.46875 pounds over 1. Remember, always a placeholder. We cancel our units of weight and we multiply and divide. So 100 times 7.46875 divided by 2.2, which gives us 339.5 calories per day for this baby. And since the caloric needs is generally a range, 100 calories is the lower part. So now we use the higher part, which is 110. So 110 calories per kilogram per day. And again, our conversion ratio and our weight, which gives us 110 times the 7.485 divided by 2.2, and it gives us 373.4 calories per day. So the caloric need for this neonate is between 339.5 to 373.4 calories per day. How many milliliters of epinephrine would you give a patient who has an order for 1 milligram every 3 to 5 minutes? The concentration is 1 to 10,000. Our order is 1 milligram per dose, and available concentration is 1 gram equals 10,000 milliliters. Remember, when you have that like X to Y ratio, it means the first number is the grams and the second number is the milliliters. So we want to find the milliliters per dose. So we put milliliters on top. So 10,000 milliliters over 1 gram. Since our order is in terms of milligrams, then we add the conversion ratio of 1 gram over 1,000 milligrams times 1 milligram per dose. The grams and the milligrams cross out, and so we multiply and divide. So 10,000 divided by 1,000 gives us 10 milliliters per dose. We have an order of medication X, 20 milligrams IM PRN every 4 to 6 hours as needed for pain. Our available is 100 milligrams per cubic centimeter in a pre-filled syringe. The child's weight is 35.2 pounds, and the recommended dosage is 2 to 4 milligrams per kilogram per dose. What is the recommended dosage range for this patient? So we rewrite what we have. So the order is 20 milligrams per dose and 4 to 6 doses per day. Available is 100 milligrams in 1 cubic centimeter. The weight of the patient is 35.2 pounds, and the safe dosage range is 2 to 4 milligrams per kilogram per dose. We are looking for the recommended dosage range, which is in terms of milligrams per dose. So we write milligrams per dose. The recommended dosage is 2 to 4. So first we're going to work with the 2. So 2 milligrams per kilogram per dose. To cancel out the kilograms, since our weight is in pounds, we multiply times the conversion ratio of 1 kilogram over 2.2 pounds times the weight, which is 35.2 pounds. Since we cross these out, we are left with milligrams over dose. We multiply the top divided by the bottom, So 2 times 35.2 gives us 70.4 divided by 2.2, which comes up to 32 milligrams per dose. That is for the lower range. So now we multiply times 4 milligrams per kilogram per dose, multiply times the conversion factor, multiply times the weight. Kilograms and kilograms cancel out, pounds and pounds cancel out. So we multiply 4 times 35.2, which gives us 140.8, and divide it by 2.2, which gives us 64 milligrams per dose. So the recommended dosage range for this patient is 32 to 64 milligrams per dose. Now, if the dose is within the recommended dosage range, how many milliliters should be administered? So if we look at what the dose is, the ordered one is 20 milligrams per dose. Since our safe range is 32 to 64 milligrams per dose, 20 is lower than 32, which is even the lowest range. So it is safe, but the dose is non-therapeutic. So since it's safe, the milliliters per dose would be, we have, for the available, they told us is in cubic centimeters, but cubic centimeters is the same as milliliters. So you can just write it as 1 milliliter over 100 milligrams. Then we want to get rid of the milligrams, so we multiply it times the order, which is 20 milligrams per dose. Milligrams cancel out, so we just divide 20 by 100, which gives us 0.2 milliliters per dose. Now, calculate the daily fluid needs for a dehydrated child that weighs 162 pounds. The oral rehydration requirement in milliliters is as follows. So for the first 10 kilograms, you need 100 milliliters. For the second 10 kilograms, you need 50 milliliters. And then you want 20 milliliters for every, like the weight in kilos minus 20, and then times 20 milliliters. So first we need to convert the pounds to kilograms. We put kilograms equals to the conversion ratio, so 1 kilogram over 2.2 pounds times the weight in pounds of 162 pounds over 1. Pounds cancel out, so we just divide 162 by 2.2, which gives us 73.64 kilograms. Therefore, okay, it says this child is dehydrated. Therefore, oral rehydration equation is used and not the standard fluid requirements equation. So there's two formulas for fluid requirements. There is one for when the patient is dehydrated, and the one for the standard fluid requirements. So since the problem specifies that the child is dehydrated, that's why we use this formula. Okay, so for the first 10 kilograms, we need 100 milliliters, so 10 times 100. For the second 10 kilograms, we need 50 milliliters, so 10 times 50. And then the total weight, which is 73.64, we subtract 20, because we already took those 20 into account here and here. So all of that times 20, which gives us 2,572.8 milliliters that we need to give the child for rehydration. Questions? Okay. Medication X is available in a powder form for reconstitution to provide 400 milligrams when 20 cubic centimeters of normal saline is added. What % solution is this? So now we're kind of working backwards. Generally, they give us the percent solution, but now we want to find the percent solution. So we have 400 milligrams and 20 cubic centimeters, which is the same as 20 milliliters. And since, for example, when we have a 5% solution, it means 5 grams in 100 milliliters of water, or 2% is 2 grams in 100 milliliters of water. We want it in terms of grams over milliliters. We have milligrams and we want grams. So we first use our conversion factor of 1 gram over 1,000 milligrams times the 400 milligrams over 20 milliliters. We cancel out the milligrams. And so we have 400 over 1,000 times 20, which is 20,000. And this gives us 0.02 grams over milliliters. Since we want it in percent though, this result we multiply times 100, which gives us a 2% solution. Questions? Okay. Insulin concentration is frequently measured as the number of units of insulin in a set volume of fluid. For example, U100 has 100 units per milliliter and U40 has 40 units per milliliter. It is possible to use a 1 milliliter, commonly referred as TB syringe, for insulin. About how much more concentrated is U100 solution than a U40 solution? So we want to know what percentage 100 is of 40. So we want to find the percentage. So 100 units per milliliter over 40 units per milliliter times 100, since it's in percentage. Our units cancel out. And 100 over 40 times 100 gives us 250%, which means that a U100, it is 250% more concentrated than a U40 solution, or 2.5 times more concentrated. Questions, because we're going into some independent problems. No? You guys are super ready? Okay, cool. Now, if you can grab a piece of paper, something to write, and a calculator, so you can work on some of these problems. So, let's see this one. We have an order of medication X for 600 milligrams IVPB every 6 hours. Available to us is 0.5 grams per 5 milliliters. The instructions are: add available medication X to a 50 milliliter bag of normal saline and infuse over 1 hour. First question is, how many milliliters of medication X are added to the bag of normal saline? B, what is the total milliliters in the IV bag after adding medication X? C, what rate of infusion should be set on the IV pump? And D, what is the rate in drops per minute when using a micro drip set? I'm going to give you guys some time to work on those. Please let me know when you guys are ready to go over the procedure. Hey guys, how are we feeling? Are you ready to go over the procedure or do you need a little bit more time? All right, let's go over it then. So for the first part, find medication X in milliliters per dose. So we've set it up as milliliters per dose. We have available 5 milliliters over 0.5 grams times we are set to order 600 milligrams to give 600 milligrams. So that means that we have to use the conversion ratio. So times 1 gram over 1,000 milligrams times 600 milligrams per dose. The grams and the milligrams cross out. And so we multiply the top 5 times 600 over 0.5 times 1,000, which is 3,000 over 500, which gives us 6 milliliters per dose. Now, how much are we going to add to the medication X bag? Sorry, how much medication X are we going to add to the bag? So we need to give 6 milliliters and the bag is 50 milliliters. So in total, the bag has to be 56 milliliters. Now we want to find the rate in milliliters per hour. So that is already that is the amount that you have to give. And it tells you that it has to be given over an hour. So it's just 56 milliliters per hour. That is the rate itself. And now we want to find drops per minute. So we want drops and we have milliliters. So we use a conversion rate of 60 drops per milliliter times 56 milliliters per hour. We want it in terms of minutes. So we multiply times 1 hour over 60 minutes. Milliliters cancel out, hours cancel out. And since we have a 60 on the top, a 60 in the bottom, those cancel out as well. So we are just left with 56 drops per minute. Of course, you could go over 60 times 56 and then divide by 60. But for me, it's easier when I see it separated like this. You see, oh, okay, I have 60 on the top, a 60 in the bottom. So it's just the same as just multiplying the 56. So that's why we have 56 drops per minute as our answer. How did you guys do? Do you have any questions? All right, then let's go to the next problem. A 5-month-old infant nipples the following amounts of formula over a 24-hour period. 90 cubic centimeters, 1.5 ounces, 5T, 45 cc, 30 cc, 3 lower T, 12 milliliters, 28 cc's, 40 milliliters, and 1.5 cc's. The caloric value of the formula is 22 calories per ounce. How many cubic centimeters did the child nipple in 24-hour period? Let me know when you guys are ready. Are you guys feeling ready? Awesome. Let's go through it. So the question is just asking us how many cc's. So we have to convert the ounces to cc. So our conversion ratio, remember that cc's is the same as a milliliter, and we know the conversion between milliliters and ounces. So 1 cc over 1 milliliter times 30 milliliters over 1 ounce, and 1.5 ounces over 1, remember the placeholder, gives us 45 cc's. Now we convert the 5T, since it's capital T, that means our conversion ratio is 15 milliliters over 1T times the 5 T's. The milliliters and the T's cancel out, and we are left with 75 cc's. Then all the milliliters, we add them and convert them to cc's, which is the exact same. Remember that cc's and milliliters are equal to each other. So if it's 52 milliliters, it means it's 52 cc's. And then we convert the lowercase t's. So 1 cc is 1 milliliter, 1 t is 5 milliliters, and we have 3 t's. So the milliliters and the t's cancel out, and we have 5 times 3, which is 15. Now that we have everything in terms of cubic centimeters, we add all of it together. So it's a lot of numbers, but you know. So 90 plus 45 plus 30 plus 28 plus 1.5 plus 45 plus 75 plus 15 plus 52 gives us 381.5 cubic centimeters. Now, with the same data, how many calories did the infant consume in the 24-hour period? As soon as you guys finish working the problem, please let me know in the chat so that we can move on to the next problem. Awesome. Let's go through this problem. So now that we have the total value of cc's, then we look at the caloric value of the formula, and we want to know how many calories per day the infant consumed. So we put calories on top, 22 calories over ounce. Then we use a conversion ratio between ounces and milliliters. So 1 ounce over 30 milliliters times. Remember that cc's and milliliters are the same. So instead of writing cc's, we can just write straight away to milliliters. So 381.5 milliliters over 1 day. So therefore, the ounces and the milliliters cross out, and we are left with calories per day, which is what we want. So 20 times 381.5 divided by 30 gives us 280 calories per day. Questions? Okay. Next problem. Since the total cc's consumed in the day was 381.5 and the total calories was 280, if the caloric requirements for a 5-month-old infant is 105 calories per kilogram per day and the infant weighs 14 pounds, how many calories does this infant require? So we already know how much they had, but we want to know how many calories they need. Let me know when you guys are ready. Awesome. Let's go over this then. So if we know that the infant requires 105 calories per day per kilogram, and we want to find how many calories per day they require. So we put the calories on top to 105 calories per kilogram per day. And then we have the weight in pounds, so we need to convert to kilograms. So times 1 kilogram over 2.2 pounds times 14 pounds over 1. The kilograms and the pounds cancel out. So we have 105 times 14 divided by 2.2, which gives us 668 calories per day. Now, it's asking us, did the infant consume the required calories for the 24-hour period? No, definitely not. If we calculated the calories the infant consumed and it was 280, and the baby requires 668. So the infant consumed less than the required calories. And then it's asking us, was the amount consumed excessive or deficient? And we know that it was deficient. By how much? And so then we just subtract 668 minus the ones that they consumed of 280. So the deficit was of 388 calories per day. Any questions? Okay, next problem. The order is to infuse dextrose 2.5 IV at a rate of 36 milliliters per hour using a microdrip set. Each gram of dextrose is 3.4 calories. How many calories is the infant receiving from the infusion per day? Okie dokes, let's go through this one. So we want to know how many calories per day. And the order was to give 36 milliliters per hour. The IV is set at 2.5 grams in 100 milliliters. And the calories of the dextrose is 3.4 calories per gram. Since it says that we're using a microdrip set, that means that our drop rate is 60 drops per milliliter. We want to find calories per day. So we said calories per day. We put calories on top. So 3.4 calories per gram times 2.5 grams per 100 milliliters. We have to give 36 milliliters per hour. There are 24 hours in a day. So we cross out the grams, the milliliters, and the hours. We multiply and divide, which gives us 73 calories per day. Any questions? Okay. Now we have two problems. So the order is to give medication X 0.16 milligrams stat. The medication label has a concentration of 2 to 1,000. How many milliliters will be administered? Then the second problem is insulin concentration is frequently measured as the number of units of insulin in a set volume of fluid. For example, U100 has 100 units per milliliter and U40 has 40 units per milliliter. 1 U of U40 insulin is how many milliliters in a regular syringe? How is everybody else feeling? Are you guys ready to go over these? Awesome. Okay. So for the first one, our order is to give 0.6 milligrams per dose, and the available is, remember, when we have 2 to 1,000, it means 2 grams in 1,000 milliliters. And we want to know how many milliliters. So milliliters equals 2, 1,000 milliliters over 2 grams, times the conversion rate from milligrams to grams, which is 1 gram over 1,000 milligrams, times the 0.6 milligrams we have to administer over 1 as a placeholder. The grams and the milligrams cancel out, and we are left with 0.3 milliliters. Yep, awesome. So for the second one, we know that U100 has 100 units in 1 milliliter, and U40 has 40 units in 1 milliliter. And we want to know how many milliliters. So 1 milliliter over 40 units times a unit is 1 syringe. So 1 over 40 is 0.025 milliliters, and if we round, it comes up to be 0.03 milliliters. Any questions? The order is for antibiotic medication X, 250 milligrams every 8 hours. Available is antibiotic medication X, 300 milligrams per 6 milliliters. The recommended dose is 75 milligrams per kilogram per day, divided into doses every 6 hours. The weight of the patient is 13.2 pounds. Okay. I was like, where's the question? Okay, so our information is the order is 25 milligrams per dose. There are 3 doses in a day because it's every 8 hours. So there are 24 hours in a day divided by 8. It means there are 3 doses a day. Available is 300 milligrams per 6 milliliters. And the recommended dose is 75 milligrams per kilogram per day, and the weight is 13.2 pounds. Now the question, what is the daily recommended dose for this patient? All right, let's go through this one. So what is the daily recommended dose for this patient? So we want to know the milligrams per day. We have the recommended dose, which is 75 milligrams per kilogram per day. And we want to get rid of the kilograms, but we have the weight in pounds. So we put the conversion rate, 1 kilogram over 2.2 pounds times the weight in pounds, which is 13.2 pounds over 1. We cancel the kilograms and the pounds, and we multiply and divide, which gives us 450 milligrams per day. So this is the daily recommended dose for this patient. Now, second question. How many milligrams is the patient getting for each day? Let me know when you're ready. All right. Let's go through this one. So we want to know how many milligrams the patient is receiving each day. So we put milligrams per day equals 2. So the order was for 250 milligrams per dose with 3 doses a day. So the doses cancel out. We have milligrams per day. So we just multiply 250 times 3, which is 750 milligrams per day. And our last question is, by how many milligrams is a daily dose excessive or deficient? Let's go through this last part of this last problem. So it's asking us how many milligrams is a daily dose excessive or deficient? So the recommended dose that we calculated before was 450. So 450 is definitely lower than the dose that the patient is receiving, which is 750. So to know how much is the difference, we just subtract 750 minus 450, and it comes up to be 300 milligrams per day excessive. So guys, this is the end of the presentation. Do you have any questions before we go and give you some more homework problems to work through?
Wow, you guys were so fast. You just stepped right through those questions one after one after one. Were you guys able to answer them correctly? Yay! That's awesome. So, like I said earlier, I'm going to send you an email with the recording of the session today. You're going to get some additional homework problems to continue working, and then a copy of the PowerPoint that Anna used. And remember, if you have any problems with any of that, you can come in and drop in with us Friday from 10 a.m. to 1 p.m. You use the same link. And good luck this semester. You guys seem like you're raring and ready to go. So looks like you're gonna do it and get it done. So congratulations. We'll see you if you need us. Okay.